Hello, and welcome back for the final video covering exponential and logarithmic functions. In this video, we're going to take a look at all the properties for exponential functions and the properties for logarithmic functions. We're going to put them all together. We're going to solve equations involving either exponentials or logarithms. And then we're going to evaluate our answers to make sure they actually work in the original problem. Remember that because we restrict the base to being strictly positive and not 1, that means the answer part must be strictly positive. Any possible solution that causes an answer part to be negative will be considered extraneous. Now, there are lots and lots of these kinds of problems, and they all work very similarly, but little tweaks make little differences here and there. The more you do, the better at them you're going to be. So we're going to take a look at quite a few here, but we'll often pause the video, give you a chance to solve it on your own. Then I'll turn the video back on and we'll compare our answers. I'll share my screen with you and we'll get started. So what we're looking at here is section 6.6 of the OpenStax Algebra and Trigonometry book. And we're looking at exponential and logarithmic equations. So there are a lot of different things that we need to talk about here, but this sort of goes through and gives you some guidelines on how to start on some of these problems. The one-to-one property is using the fact that both an exponential and a logarithmic property are one-to-one. Every x has exactly one y value. Every y value belongs to exactly one x value. If that's the case, then let's say that I take b and raise it to the s power, and I get b raised to a different power t. Well, if they're equal to each other, then the answer parts are equal and the bases are both b, so the bases are equal and the answers are equal. Then because it's a one-to-one function, that means that the powers also have to be equal. So we can solve this by setting s equal to t. So we want to take a look at an example problem here, which we can see right here. We have 5 to the 2x equals 5 to the 3x plus 2. The equals means that they are already equal. So our answer parts are equal. Our bases are both 5. And that means the powers have to be the same by this one-to-one property of exponential functions. So from here, I can directly write 2x equals 3x plus 2 and solve for x. So subtracting the 2x from each side and adding the 2 leads to 2 equal to x. Now, I have to make sure that this is actually going to work. So when I look back at the original problem, I identify where the x variable occurs. If it's in the base or in the answer part, there are restrictions. If it's in the power, anything goes as long as it's real, which means that my solution is, in fact, x equal 2, right? There are no restrictions on the power other than it be a real number. So what does this actually mean? This says 2 times 2 would give me, oops, did I solve that correctly? Let's take a look at this again. Oh, I should have subtracted 2. That makes more sense. I knew I had an error. So sometimes it's just as valuable to know why you have an error. How did I know I had an error? I was checking my result and I was checking 5 to the 2 times 2 to see if that came out to be 5 to the 3 times 2 plus 2. They didn't come out the same. So I knew I had a mistake. So I went back and checked my work and saw that I had added 2 instead of subtracting it. This is going to give me x equals to negative 2. Now, if x is negative 2, let's check that because this one didn't work. I found my error. So now I come back and I have x equal to negative 2. So I have 2 times negative 2. Does that really equal 5 to the 3 times negative 2 plus 2? 3 times negative 2 is negative 6. Negative 6 plus 2 is negative 4 on the right. And on the left, 2 times negative 2 is also negative 4. So in fact, they are equal. So it's just as important that you know how to fix your error as it is to be able to identify the error. So I'm actually glad I made that mistake. Let's take a look now at a slightly different problem where the bases are not the exact same number. So in the problem on the left, we have 5 equal to the 2x equal to 25 to the 3x plus 2. So the bases are different numbers. One is 5 and one is 25. However, they are both powers of the same number 5. So if I can write them as both powers of 5, I should be able to solve it. So I'm going to leave the one on the left as 5 to the 2x, but I'm going to rewrite my 25 as 5 squared. Now that was being raised to the 3x plus 2 power. So now I essentially have 2 powers on the base 5 on the right. The rule is if you have one base and 2 powers, you multiply the powers. So this is going to give me 5 to the 6x plus 4 equal to 5 to the 2x. Then I know that the answer parts are equal. That's what the equals in between means. The bases are clearly both 5. And that means because it is a one-to-one function that the powers have to be equal. So 2x has to equal 6x plus 4. And I'm going to make sure I don't make a mistake this time. So I'm going to subtract my 2x from both sides. And then I'm going to subtract my 4 from both sides. And I get 4x equals negative 4 or x equals negative 1. Now, does that work? So let's check it. So we're going to do a check on each one of these. So I have 5 to the 2 times negative 1. Does that give me 25 to the 3 times negative 1 plus 2? 3 times negative 1 is negative 3 plus 2 would give me negative 3 plus 2 is a negative 1. So I have 25 to the negative 1 equal to 5 to the negative 2. Now I can look at this one and say, oh, well, I could also think of this as 5 to the second power raised to the negative 1 power. If I can go one direction, I can go the other direction with exponents. And 5 squared is equal to 25. So I have 25 to the negative 1 on both sides, or 1 over 25 equals 1 over 25. What about this problem on the right? This problem on the right is a little bit different than we sometimes see. On the left, the base is 5, and on the right, we have square root of 5. But remember that square root of 5 can be written as 5 to the 1/2 power. So I can rewrite this one as 5 to the x equals 5 to the 1/2. And then the answer parts are equal. The bases are both 5. It's a one-to-one function. So the powers have to be equal, and x has to equal the 1/2 power. Let's take a look at this one right here and consider whether or not exponentials always have solutions. When we're looking at this one, I actually went ahead and I graphed y equal 2 to the x in red, which you can see it coming down here up on the y-axis, coming down, and then it makes this turn, and it gets very close to the x-axis. But remember, it never touches or crosses it. It cannot actually come out to be 0 because the base is a positive 2. And of course, our domain is going to be from negative infinity to infinity, but our range is from open 0 to infinity. The right-hand side is the equation y equal to negative 100. And I had to zoom out quite a bit to get that one to show up. So let me write that down in blue. And the question is, do these two graphs that we see here in the picture, do they ever touch or cross? We're looking for where they're equal to one another, which means they have to intersect. There has to be a point where they touch. But there's not one. Remember that this red graph, the exponential 2 to the x, approaches the x-axis but never touches or goes below it. And this horizontal line, y equal negative 100, never tilts up. So they're never going to touch or cross. This brings up an important point, which is that not all exponential equations have solutions. This is one that has no solution. So you can write DNE, which stands for does not exist. There is no solution. So we write DNE. Sometimes you can also write none, right? So when we're looking at this, think about what led to this result. I took a positive number 2 and I raised it to a power. Remember that the answer parts can only be strictly positive because the base is positive. That means I have a positive equal to a negative, which I know has no solution. Now we want to take a look at ones where the two sides cannot be written as powers of the same number. They're not going to both be 5, for example. If we're looking at this one right here, we have 2 to the x power on the left and 3 to the x plus 1 power on the right. Again, not all of these are going to have a solution. Some do, some don't. We'll just have to see. When we're looking at this, we tend to look at the bases and see if we have either a base 10 or a natural log. If either one is a base 10, we might use the common log base 10. Otherwise, we tend to use natural log. So what we're going to do, because these are not powers of the same number, we have to use logarithms to help us solve. So what we're going to do is we're going to apply the natural logarithm to both sides of the equation. So we're taking the 2 to the x and applying a natural log operation to it. And then we do the same thing on the right side. Right? So we have now 2 natural logs equal to one another. The natural log, like the exponential, is a one-to-one function. So as long as I apply it on both sides, I haven't changed the solution. Now I can use the properties of logarithms to pull the variable out of the power down to the line so I can get my hands on it, right? Because in the original, the variable x, which is what I'm looking for, I'm trying to solve for x equals something, it's way up in the power. I can't get my hands on it. There's nothing you can do algebraically, add, subtract, multiply, divide, raise, take a radical. None of that's going to pull the x down. But the property of logarithms, as the power property, does do that. So now I apply that power property. So that's going to be the next thing that I'm doing. I apply that power property. It pulls the x to the front, and I have natural log of 2. Now remember, natural log of 2 is one number, natural log of 2, right? All of that represents the power on E to get the number 2 as the answer. On the right-hand side, the power on the answer part is the group factor x plus 1. So it needs to go in parentheses, and then it gets multiplied by the natural log of 3. Now I've got 2 terms here that have x in them, but the x's come down to the line. Do you see how in the problem here it's up in the power, but using that power property of logarithms, I brought it to the line. Now I can add, subtract, multiply, divide, and do those things to get my hands on it. What I'm going to do is multiply out the right-hand side using the distributive property. So on the right-hand side, this gives me x times the natural log of 3 plus 1 times the natural log of 3. And this is equal to x times the natural log of 2. Now, this is a more challenging problem. This is actually somewhat difficult, right? But when you get into calculus, if your pathway takes you to calculus, you need to be able to solve these kinds of problems. It's going to happen more than once. It's going to happen quite often. So what I want to do now is I want to get these two terms together here. So I'm going to subtract the entire term, x times the natural log of 3, from both sides of the equation, right? Now I'm going to write it out so that we can see what it looks like. So I have x times the natural log of 2 minus x times the natural log of 3 equals the natural log of 3. Now, I have two terms with x in it. X is what I want to solve for. So even if I had another common factor, I only want the x. I want to pull the x out by factoring it out, and that leaves natural log of 2 minus the natural log of 3 equal the natural log of 3. Now, the next thing that I can do when I'm looking at this is I have a natural log of 2 minus a natural log of 3. They're both base e, and they're subtracted. So this must actually be the natural log of 2/3. So I can combine those together. And then on this side, I have a natural log of 3. Now, you know what's coming next. This is x times the natural log of 2/3. So I'm going to divide both sides by the natural log of 2/3. And I get my final solution. X equals the natural log of 3 divided by the natural log of 2/3. Now, it's very tempting to want those natural logs to cancel, but they don't. Each one individually represents a single number. So they're not a symbol that can be canceled out. The 3's do not cancel either because they're not actually 3's. They're inside a natural log, which represents a totally different number. So this is as far as we can go with this problem. This gives us our value, but we can take our calculator and we can enter it in here to find what this is equal to approximately. So when we do that, we would enter parentheses around the natural log of 3, and then we would divide by parentheses around the natural log of 2/3, and I would put parentheses for sure around the 2/3 as well. And this gives me roughly, scroll up a little bit more. I'll have to round off. This is a negative 2.70951 ... Now I'm going to store this value because I want to check it and see if it actually works. So store A, remember we always have to look for solutions that don't actually work. And I want to take 2 and raise it to that power. So I'm going to put in 2, hit the caret symbol for the power symbol, or y to the x or x to the y. And then I'm going to recall that value for my power. And I got that 2 to the x was roughly equal to 0.152881814 ... Now, I'm going to take 3 and I'm going to hit the power symbol again. And then I'll put parentheses around it. And I'm going to recall that value, add 1 to it, close the parentheses, hit equal, and I get that value again. So I know that they are equal and that that value of x does solve the problem. And again, how do we know it's not a false solution? The value x, the variable, was in the power. As long as it turns out to be real, it will always work. Anything goes in the power as long as it's real. Now I want to take a look at this type of problem. These are very common. You see these in continuous growth problems or continuous decay problems. So if we're talking about the half-life of a radioactive material, then it would be a decay problem, or the growth of a continuous compounding or population growth. We get this a e to the kt equal to y. Right? Often we write it as a of t equal p e to the kt, where the coefficient of the e to the kt is the present value or the principal amount. Now, if we're given one of these, how can we take this equation and get our hands on that t, right? I mean, that's what we're really trying to do. So we come over here and we look at it like this. And in order to get our hands on the t, I'm going to have to apply that logarithm property that pulls the power to the line. But before I can do that, I need to isolate things. I can also switch forms and I can go to logarithmic form. If I go to logarithmic form, then I need to move the a first so that I've isolated the exponential. So one option is to take y, divide by a, and have this equal e to the kt. Then once I have this, I can switch forms. Remember, this is my base, this is my power, and this is the answer part. And I can switch the form and say that the natural log of y over a is equal to k times t. And now I've got the t down to the line, so I can solve for t by dividing both sides by k. Now, when we divide a natural log by k, you either need to use a large division bar or write 1 over k out front. So the two options that I recommend are the natural log of y over a, all divided by k. That's one option. But I really think it's better to write 1 over k times the natural log of y over a. And of course, you can also stretch out the y over a little bit and make it natural log of y minus the natural log of a. Now you can also solve it by taking the natural log of both sides of the equation, and that will likewise solve it as well. So let's take a look at that real fast. If I had taken the natural log of both sides, and I would have used natural log, not common log, because the base is e, then this would give me the natural log of a times e to the kt. But I have multiplication in the answer part, so I can split the right into the natural log of a plus the natural log of e to the kt. But the base of natural log is e, and the answer part is e to the kt power. So this part just becomes kt. And then I can move this to the other side, and I will have natural log of y minus natural log of a equal to kt, and then I divide by k, which in essence gives me exactly the same thing I had previously. So how can I apply this in a real problem? One of the things that I do is I like to switch forms, so I tend to do that more often. So I'm going to divide by the 3, and this is going to give me e to the 0.5t equal to 11 thirds. Then I'm going to switch forms from exponential to logarithmic. The base is e, so I'll use natural log. The answer part was 11 over 3. And it equals the power, which was 0.5t. And then to solve for t, I need to multiply both sides of the equation by 2. And that then will finally give me that t is equal to 2 the natural log of 11 over 3. I could pull the 2 in as a power on the 11 thirds. It would become 121 over 9. And then I could use my calculator to find that value. So when I do this one, I get 2 times natural log, open parentheses, 11 divided by 3, close parentheses. And I have that t is approximately 2.59856, blah, 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 blah. Okay. Now, how do I know this worked? Remember to look to see which part the variable is coming from. In this case, t is the power, so long as it's real, it works. I got a real, it works, unless I made a mistake, which does happen as we've seen already. So let me go ahead and check it. So what I'm going to do is I'm going to put in e to a power, which is the second function above the natural log. So when you're looking at your calculator, identify ln and look above it. Hit the button that gives you the second function and then the ln key. And I'm going to raise it to the 0.5 times, and I'm going to recall that last value. And then I'm going to multiply it by 3 and see if I get 11. So I forgot to store my value. So store A. So starting back over again, I'm going to have the second ln to get e to a power. And then the power is going to be 0.5 times recall A. And then I'm going to multiply that by 3. And I should get 11. And I did. Okay. So I always kind of like these. I think they're kind of fun. They're like a little puzzle. So I've always kind of enjoyed them. Now, that being said, this next type is actually kind of hard, all right? So it can be difficult to recognize. So I want to let you know how to recognize this is what's happening. This is what we call something quadratic in form, which we've seen before this semester. This time it is quadratic in exponentials. So it's not really a quadratic equation, but it behaves like one or takes on the pattern of one. So how do I know it's quadratic in form? First off, notice that I have x and I have double that. If I have double that, this is actually e to the x squared. Why is it e to the x squared? If I take e to the x and I square it, remember that is one base, two powers. You multiply the powers. And so this gives me e to the 2x. So this power on the first term is double the power on the second. Whenever you have that kind of situation, it could well be quadratic in form. So I'm going to make a substitution, and I'm going to substitute u to be equal to that lower powered one, the original e to the x. So this then becomes u squared minus u equal 56. Subtract the 56 to the left side of the equation so that it equals 0. Then we can factor this. We need two factors of 56 that subtract to give me a negative 1. So it's got to be u and u to give me u squared. One of them's got to be 8, one's got to be 7. To end up with a negative u, I need a minus 8 and a plus 7. And then I can solve these individually. And this gives me the two possible solutions, that u equals 8 or u equals negative 7. Now, when you start one of these, what you should probably do up at the top is put x equal and draw a blank. I have u values. That is not what I want. I want x values. And x was in the power, so as long as they turn out to be real, they'll work. So now what I have to do is back substitute or unsubstitute. So what I have here is e to the x equals 8 or e to the x equals a negative 7. Now this is going to introduce a false solution. Look at this right here. E to the x has to be strictly positive. The answer part's always going to be positive, but this is a negative. Positives do not equal negatives, and so this is just false. There's no solution here. Does not exist. That can never happen. What about the one on the left? Well, sure, I can switch forms and I can go to the logarithmic form, or I could take the natural log of both sides and use the power property to pull the x to the line. Either way, I have the natural log of the answer 8 equals the power x, and this is going to be the only solution to my problem. So remember, you can always get a false solution if you have an answer part or you have a base. The base has to be positive, not 1. The answer part has to come out to be strictly positive. And for powers and things like that, the only thing that can happen there is that you get something that's not true, like a positive equal to a negative. That will not give you a solution. So again, just to reiterate, not every logarithmic equation has a solution, just as not every exponential has a solution. We want to take a look at this next one now. This is going to use algebra to solve this. Now, we were solving exponential problems. Now we're switching to logarithmic. So when we're switching to logarithmic, we're going to do very similar steps. We're going to isolate the logarithm, and then we're going to switch forms from logarithmic to exponential and see if that helps. So the first thing I need to do is isolate the natural log. So I'm going to subtract 3 first. And this gives me 2 natural log of x equals 4. And then I'm going to divide by 2. So I need to isolate the natural log of x by itself. So the next thing I'm going to do is divide by the 2. And this gives me the natural log of x equals 2. And once I have the natural log isolated, I can switch forms. And this says e squared equals x. And so I end up with one solution, which is e squared equal to x. Now, when you're looking at the problem this form, you'll notice that there's only one possible solution because this is what I had in the original. Now, you may say, yeah, but you could have pushed that 2 inside. I could, but that actually changes things a little bit. So let's see how it changes it so that you can see what it looks like if you solve it in a different fashion. If I had pushed that 2 back inside, I would have changed the answer part from x to x squared. Now, x squared is always going to be positive as long as it's not 0. But x is not, and that may introduce a false solution. So then I have the plus 3 equals 7. So I subtract the 3 from both sides, and I get natural log of x squared equals 4. And then I would have this e to the 4th equals x squared. Now we would go ahead and we would take the square root of both sides. I have x squared, so when I take the square root of x squared, I get a plus or minus on the other side. The square root of e to the 4th is e squared. The question is, can we use both the positive and the negative? The answer is no. We cannot use the negative because if we plug it into the original equation, it would give us a negative answer part. So negative e squared is extraneous, a false solution. It does not actually work. The only solution is e squared, right? One method that never happens, the other method, it introduces a false solution. Basically, squaring things is kind of a risky thing to do. We can also use the one-to-one property of logarithms to solve logarithmic equations. We can also solve those by combining all the logarithms together and then switching forms. It can be done both ways. So when you apply this property, they both have to have the same base, which here is b. And if they're equal to each other, then the powers are equal and the bases are equal. And that means that the answers have to be equal. So we can solve a problem doing this method right here. So in other words, if I had something that looked like log base 5 of x equals log base 5 of 2, then I know that x has to equal 2, all right? Has to be that 2 value because the powers are equal, the logs are equal, and the bases are equal. Now let's take a look at this problem, which is another challenging one that may have a false solution. So I have natural log of x squared equals natural log of 1. So I graphed the natural log of x squared in red. So this is y equals the natural log of x squared. And you'll see it has this shape kind of like well, it's like how small children draw birds in the sky, right? So it comes in and comes to a point and then it comes out again. Now we know that x can't be 0, so it's actually approaching the y-axis as a vertical asymptote from both the left and the right. But because the answer part is squared, x could actually be positive or negative. And when you square it, the answer part will be strictly positive. Now, the natural log of 1, that's one of our properties. We happen to know that the natural log of 1 turns out to be 0, because the only way to get 1 for the answer part is to have a power of 0. Now we're looking for where these intersect so we can see that we have a -1 and a 1. Now, if we applied the one-to-one property of natural logs, we would say, well, the bases are both e here, and the natural logs are equal, so the powers are equal, therefore the answer parts have to be equal. And you can take the square root of both sides with a plus or minus on the non-variable side, and we get x equals plus or minus 1. And we have to check each individually in the original problem. But this time when we're checking, the answer part is squared. The 2 is not brought to the front. It's a weird thing, and you have to be very careful about this. But 2 natural log of x and the natural log of x squared have different graphs, because the domain of this one is 0 to infinity, and the domain of this second one is -infinity to 0 union 0 to infinity. They do not have the same graph. Be very careful. Algebraically, they're very close, but if you're solving for x, they're going to have different domains. So you have to be careful about that. In this case, both 1 and -1 square to give me a positive answer part, so both work. And you can see that, in fact, those two curves do touch each other in 2 places at -1, 0 and 1, 0. And that's what we're doing, is we're finding where 2 curves intersect. I want to talk just briefly about half-life. We're not actually going to do any of these problems in the homework set, but you may encounter this in one of your classes in chemistry or physics, and you need to understand how to do it and what it actually means. So let's take a look at one of these up here, and it uses this term half-life. And what does that mean? These are all radioactive substances. So a radioactive substance is something that, well, one, it will kill you, right? So it's dangerous to be around radioactive material for any length of time. The larger the amount of material and the longer you're exposed, the more damage is done to your body. So when we're looking at this, gallium-67, which is the first one up here in our list, has a half-life of 80 hours. So what does that mean? Well, let's suppose that we started out with 1,024 grams, which is actually not very much, but is easily enough to kill you, all right? If you carried this around in your pocket for a while, you would be sick, all right? So if we look at this, what does this mean? So this is going to be time over here, and we're looking at how much we have left. So if time equals 0, I have 1,024 grams. After 80 hours, so this is all going to be in hours, after 80 hours, half of that gallium-67 is no longer radioactive. It has undergone a chemical process where it's no longer radioactive, but half of it is still radioactive. So I still have 512 grams of radioactive material at the end of 80 hours. Now, another 80 hours goes by, and you may say, well, then I'm safe, right? Because then another 512 stops being radioactive. That's not how half-life works. Half of what was there the last time the time period changed is no longer radioactive. So it's half of the 512, which means that I still have 256 grams, plenty to kill you, is still radioactive. Okay, so another 80 hours goes by. So now we're up to 240 hours, which is quite a few days. And half of the 256 is now still radioactive. So if I take half of 256, that's 128. So I still have 128 grams of radioactive material. Another 80 hours, so 320 hours goes by, and half of the 128 is still radioactive, 64 grams, plenty to kill you. And then another 80, so I'm up to 400 hours here. Half of the 64 stops being radioactive, so I still have 32 grams of radioactive material. And you may say, well, yeah, but eventually you're going to get to nothing. No, you don't. You never get to nothing. You just get to something you can't measure easily anymore. After 480 hours, we still have 16 grams, which is still plenty to kill you. And then after 560 hours, we still have 8 grams, plenty deadly. And after 640 hours, we still have 4 grams, plenty to make you sick. And then after another 80 hours, up to 720, we still have 2 grams that are radioactive. And moving up to 800 hours, this is still 1 gram that's radioactive. And you may say, okay, well, then I'm done. Oh, you're not done. 880 hours, half of a gram is radioactive. Then it will be 1/4, then 1/8, then 1/16, 1/32. You will never get to 0, right? This is why accidents like Chernobyl and the accident in Japan are so serious. That material never gets to 0. It never completely stops. When we solve these problems, we generally put them in a format like this. This A sub 0 represents the amount initially present. So for our example, that would have been our 1,024 grams. And then the base of the exponential is the half-life itself, the 1/2. And then it's raised to a power, T divided by the half-life. The half-life of gallium-67 is 80 hours. And this T has to be measured in the same units. So for example, if I wanted to put in the 400 hours, and I wanted to figure out how much was still going to be radioactive after 400 hours, we've already figured it out one way, but now we can do it this way. This would give me 1/2 raised to the 400 divided by 80, which would give me 5. So I have 1,024 times 1/2 to the 5th power, and you can use your calculator or you can work it out in another fashion, however you want to do it, and you will come up with, let's see, I'm going to do 1,024 times 0.5 raised to the 5th power, which is 32. Which is the same thing that we got previously when we were just counting down, right? But this would allow me to figure out how much is still radioactive at any point in time. Okay, there's one more problem I want to take a look at just to practice this a little bit. We have the natural log equal to the natural log. The bases are both e, the powers are equal, so we know the answer parts have to be equal. So this means that I can write -3x equals x squared minus 6x. And then I can move the -3x to the right, so I can solve the equation, which gives me x squared minus 6x plus 3x equals 0. Which gives me x squared minus 3x equals 0. Factor out the x and get x times x minus 3 equals 0. So x equals 0, or x equals 3. Now come back over here and look at your answer parts. The domain of this one is that negative 3x has to be greater than 0. And if I divide by the negative 3, remember that reverses the inequality, which basically means that x has to be less than 0. And that makes sense because if I'm going to multiply by a negative 3, I need to multiply a negative by a negative to make that answer part be positive. So x should be negative. On this one right here, so this one is negative infinity up to 0. This domain is going to be different. It's going to be whatever is the domain of x squared minus 6x, whatever makes that positive. And remember that we solved these in the previous chapter, looking at this, whatever makes x squared minus 6x positive. So this becomes x minus 6 has to be strictly greater than 0. So we write these in a row, and then we write the combination at the bottom. X changes signs at its solution of 0. So it's going to be negative on the left and positive on the right. 6 changes signs up here at 6. So this one's positive on both sides and 0. And it changes signs. I need to move this a little lower. This changes signs at 6. So it's negative here and positive up here. And then we multiply the signs together to get a positive, negative, positive. So if I want it to be greater than 0, I can take negative infinity up to 0, union 6 to infinity. But notice that it's got to fall within both of these, which means that it's going to have to be between negative infinity and 0. This x equals 0 is extraneous. It does not work because in the original, if it were 0, this would be 0 for the answer part, which is not allowed. 3, does 3 work? Well, if I plug that in, I get negative 9. Am I allowed to have a negative 9 as an answer part? No, you're not. So the fact is, these are both extraneous. So is there a solution? No, in fact, there's not. There's none or does not exist. No solution to this problem. I think we're now ready to go ahead and start looking at the homework problems. I'm going to go through these relatively quickly, and I'm going to pause the video often so that you can work them out on your own, and then turn the video back on to compare our answers. I won't go into a deep explanation of each one, but I'll give you enough time to pause the video and see my work. So let's go ahead and get started on the homework. In problem number 1, we have 16 times the exponential 4 raised to the 5x power equals 256. Notice that the 16 is not a part of the base or the power or the answer part for this exponential factor. That means that I should probably divide both sides by 16 to isolate the exponential first. When I divide by 16, on the right-hand side, 256 is divisible by 16. I believe it does give you 16. I think that 16 squared is 256. It is, so we end up with 4 to the 5x power equals 16. Now I know that 16 is in fact a power of 4. So I'm going to write the right-hand side as a power of the same base as the left side. I could also switch to 2 since they're both powers of 2, but I might as well stick with the easiest, which is 4. Now that I've got the answer parts equal and the base is equal, it's a one-to-one function. So the powers must be equal. 5x equals 2 or x equals 2 divided by 5. Go back to the original to see where it came from. It came from a power. So the variable is in the power. So long as it is a real number, it should work. You can plug it in to check your work and make sure that this does in fact give you the same value. Right? So 4 times, or 4 raised to the 5 times 2/5 power. The 5's cancel, and that gives me 4 squared. So I have 16 times 16, which does give me 256. Always be on the lookout for extraneous solutions. So let's take a look at problem number 2. I'm going to leave you to work this one out and then turn the video back on to compare. I used the property for powers that when the bases are the same and we're dividing, we subtract the denominator power from the numerator. That gave me 2 to the x minus 3 equals 2 to the 7th. They're both powers of 2. The base is 2 in both cases. So I set the powers equal and solved. Then I checked to make sure it did in fact work. Let's look at problem 3. Problem 3 is a little bit more challenging. This x squared minus 5x plus 9 is all in the power on the 2, and we have an 8. 8 can be written as a power of 2. Give it a try, then turn the video back on to compare your answer. On this problem, because the power was quadratic, I was able to write the 8 as 2 to the 3rd and then set the powers equal. Then I moved the 3 to the left, rewrote the quadratic, and then factored it. It gave me 2 possible solutions of 3 and 2, and they both checked to give me the correct answer. So the solution is in fact both x equal 3 or x equal 2. Okay, let's take a look at problem number 4. In problem number 4, we again want to try to use like bases. This is a little bit more tricky. So this one is a little bit harder in some ways than the one that we just did. So when we're looking at this problem, I've got 1/4 to the 3x power. So I can think of the 4 as a power of 2, 1 over 2 squared. So the first thing I'm going to do is I'm going to rewrite the 4 as 2 squared, and then it's raised to the 3x power. The 8 can be written as 2 to the 3rd power. And on the right, I already have a power of 2, 2 to the 5th. Now, how can I rewrite this 1 over 2 squared so that it's just a power of 2 and not in a fraction? Well, it's in the denominator, but I'd like it to move to the numerator. So I changed the sign of the exponent from positive 2 to negative 2. Then I'm going to use the property of exponents that says when you have one base and 2 powers on the base, then you multiply the powers. So this gives me 2 to the negative 6 times 2 to the 3rd equals 2 to the 5th. Now I can use another property of exponents that says if you multiply and the bases are the same and each base has a power, then you add the powers. So this gives me 2 to the negative 6x plus 3 equals 2 to the 5th. Finally, because they're equal, the answers are equal, the bases are both 2, so the powers have to be equal. So I have negative 6x plus 3 has to equal 5. And then I solve for x. So solving for x, I'm going to have a negative 6x equal to 2. And then I divide both sides by negative 6, and I get x equals a negative 1/3. Now, does it work? Yes, in fact, it does work. The x was in the power position. 3 times 1/3 would give me 1, and it was negative. So this is 1/4 to the negative 1, which is going to become, is that correct? Negative 1, which would make it 4, So then I'd have 4 times 8, which is 32, which is 2 to the 5th. So yes, it was correct, and it does work. Right? So now I'm going to take a look at problem number 5, where we need to use logarithms. because these are not powers of the same base. I have 8 as the base on the left, and the right is a number 1. So those are not both powers of 8, not both powers of 2. So in this case, I have to use logarithms to try to solve. And what I'm going to use is the natural log. Neither one is base 10, so it makes more sense to use natural log. So I apply the natural log property to both sides of the equation, the natural log operation. And on the right, I get the natural log of 1, but I know the natural log of 1 becomes 0. So now I have an x or a logarithmic form, so I can switch and go to exponential. So now I'm going to go back to exponential. So I have e to the 0th power equals 8 to the x. Oh, well, that just gets me back where I started. So I don't want to do that. Does everybody see that that would just put me in a circle and put me right back up here, which gets me nowhere? So that tells me that's the wrong way to go. Well, what else could I do besides switch forms? I need to get the x to the line so I can solve for it. So let's pull the power on the answer part to the front using our logarithm property. So this gives me natural log of 8, and it's equal to 0. Then I can apply the distributive property. So I have x times the natural log of 8 minus 4 times the natural log of 8 equals 0. Move the 4 natural log of 8 to the right-hand side. I get x natural log of 8 equals 4 natural log of 8. And then I can divide both sides by the natural log of 8. And the natural log of 8 group will cancel out, and I get x equals 4. Does that make sense? Well, yeah, it does. If I look at the original, 8 to the 4 minus 4 is going to give me 8 to the 0, which equals 1. So it does, in fact, work. All right. So notice here that we almost went in a circle and didn't help. So we backed up a step and applied a different property of logarithms that would enable us to get the x down to the line. Now let's look at property or problem 6. We're going to use logarithms again because we're trying to solve the equation 6e to the 2x equals 10. The base on the left side is e, and on the right we have a 10. Even if we were to isolate and divide by 6, 10 divided by 6 is 5/3, it's still not e. It's not a power of e. So we're essentially looking to see where the graph of y equals 6e to the 2x, which is here in red, crosses the graph of y equal 10. So we're looking for that intersection, and they do intersect. And I believe I got it on the right spot. So we'll see if it comes out to be that value. So the next thing we need to do is the variable is in the power. So we're going to isolate the exponential, and then we're going to take the natural log of both sides, or we can switch to natural log form and pull that power to the front, however we want to look at it. So the first thing I'm going to do is divide by the 6, and that gives me e to the 2x equals 5 divided by 3. Now, if you want to take the natural log of both sides, you can, or you can just switch forms. So this has base e, so I use natural log. The answer part is 5/3, and it equals the power 2x. So to solve for x, I just need to divide by 2. I like to write it as 1/2 times the natural log. So I actually end up with this right here. And because it is a coefficient now, I could pull it on the inside as a power. So what I really have in here is 5/3 to the 1/2 power, but the 1/2 power is the square root. So really what I have is the square root of 5/3. So however you want to think of that, take your calculator, calculate that value out. You can leave it up here in that form if you prefer that. So I'm going to do 0.5 times the natural log, parentheses, 5 divided by 3, close parentheses, and I got about 2.55412811, which is exactly what we see right here, right? So x is approximately 0.2554128 ... right? Keeps going. All right, let's move on to the next problem, which is problem number 7. Problem number 7 is a little bit different than the others because we have a non-exponential term on the left, -6, and a non-exponential term on the right, -24. So the first thing we want to do is isolate that exponential. So I'm going to take the equation e to the r plus 12, and I'm solving for r, and I'm going to move the -6 to the right side by adding 6 to both sides. Isolate the exponential or the logarithm first. That's a good first step. And this gives me -18, but I'm going to stop right there because I already know there's not going to be a solution to this. E to a power has to be positive. And I have a negative, and positives do not equal negatives. It does not exist. There is no solution. So we will write none. All right. So let's take a look now at problem number 8. While I'm waiting for it to save, because if I try to scroll, it always messes up. So we have to wait for it to save. It's being very pokey. All right, now we'll look at problem number 8. I've got two terms that are not part of an exponential, the -11 and -29. And I've also got a -2 multiplied by my exponential 2 to the p plus 14. So let's see if we can clean this up and if it will make sense. Now, in our last problem, we saw that e raised to a power is strictly positive. It can't equal a negative. Let's see what happens here. So we have -2 times 2p plus 14. And then I had the -11 equals -29. So I'm going to add 11 to both sides. And that gives me -2 times 2p to the 2 to the p plus 14. And that's going to equal a -18. Now you can go different ways from here, but for me, what looks like the easiest is to go ahead and move this -2 by dividing both sides by -2. So I'm going to isolate my exponential by dividing both sides of the equation by -2. And this gives me 2 to the p plus 14 equals 9. Now this is possible. A 2 raised to a power will give me a positive, so it's quite possible that this works. But notice that this is 2 and this is a 9. Now 9 can be written as a power of 3, but not as a power of 2. So I need a natural log to help me. So I'm going to take the natural log of both sides. So I have 2p plus 14, I lost my 1, equal to the natural log of 9. Use the power property for logarithms to pull the p plus 14 as a factor to the front, multiplied by the natural log of 2. Then we want to divide both sides by the natural log of 2 so that I can isolate my p plus 14 to become the natural log of 9 over the natural log of 2. Now remember, I cannot cancel the natural log. This is not one natural log. This is a natural log divided by a natural log. And then the last thing I want to do is subtract 14. So I get p equals -14 plus the natural log of 9 over the natural log of 2. Now I can put this into my calculator. You can also write it as natural log of 9 over natural log of 2 minus 14, whichever one you think is best. And I've got -14 plus quantity natural log of 9 divided by quantity natural log of 2. and I got about negative 10.830075, and it probably keeps going from there. So if I want to decide whether or not this works, I can plug it back into the original and see if it gives me the same value. Because the p came from the power, and because we isolated the exponential and had it equal to a positive, it almost certainly does work. But let's go ahead and store it. And then I can do 2 to the power, recall that power, add 14 to it, equals, times a negative 2 equals, minus 11 equals, and I got negative 29. Let's move on to the next problem. On problem number 10, we can see that we have a term 3e to the 5x and a term e to the 10x. The 5x, if you double it, gives you 10x, which means this one's probably quadratic in form. So make the substitution that u is equal to e to the 5x, which means u squared is equal to e to the 10x. Then you will be able to write it as a quadratic equation, move everything to one side with 0 on the other, factor and solve, and then check to make sure your solutions work. Go ahead and do that, and then turn the video back on to see if our answers match. Don't forget on this type of problem to write down x equal blank to remind you that after you've solved for u, you have to back substitute to solve for x. When we make the substitution, we get a quadratic equation which can be factored and solved. We get two possible solutions, 5 and negative 8. When we back substitute that u is e to the 5x, the negative 8 solution is false since a strictly positive value can't equal a negative. The other one, when I put it in, I can put it into natural log form to get natural log of 5 equals 5x, and then I can multiply both sides by 1/5. I can check this in my equation over here. Notice that 10 times the 1/5 natural log of 5 will give me 2 natural log of 5. Then I can pull the 2 in on top of the 5 as a power, which gives me the natural log of 25. Now the e and the l are back to back and they undo each other, so this just becomes 25. When I plug it into the middle term, I get 5 times 1/5 natural log of 5, which gives me natural log of 5. So the natural log and the e are side by side, which gives me 3 times 5 or 15. 25 plus 15 is 40, and 40 minus 40 gives us 0. So the solution does, in fact, work in this particular problem. Now let's take a look at problem number 11. As soon as my computer stops saving. Come on. It's taking a while. Okay. Now let's take a look at this problem here. Go ahead and pause the video, work it out, and turn the video back on to compare. This one was kind of a challenging problem. How'd you do on it? Go ahead and pause the video and look through my work to make sure that you understand how to isolate the exponential first, and then switch to natural log form in order to solve for k. You'll see that I've written small notes of what I did for each step down by the side, and then I substituted in the original to check. Again, assuming that k is a real value, then I know that as long as it's equal to a positive, I'm not likely to get a false solution on an exponential equation. Now we want to switch gears and we want to focus on logarithms. So when we're looking at this equation, we're trying to solve the equation 9 times the logarithm base 2 of x is equal to 18. There's more than one way to go here, but the easiest thing to do is first to isolate the logarithm. So I'm going to divide both sides of the equation by 9. This will lead to log base 2 of x is equal to 2. The next thing I'm going to do is switch from logarithmic form to exponential form. I've isolated the logarithm, so now I can switch. So I'm going to switch forms. This gives me 2 to the second power equals x. So I get x equals 4. Now I have to be more careful here than I did in the exponential equations because it is more likely to get a false solution here because the variable is coming from the answer part. Remember that the domain here is going to be from open 0 to positive infinity, but 4 does lie in that region, so it is going to work, right? And again, you can check the answer in the original. What we're looking for here for a false solution is something that would cause the original problem's answer part to be negative. Let's now look at problem 13, where we have 4 plus the log base 9 of 8x equal to 3. Again, I want to isolate the logarithm as my first step. That means I'm going to subtract the 4 from both sides of the equation. And I get logarithm base 9 of 8x equals a negative 1. Now, before you freak out and go, oh, that's not possible, remember the log is equal to the power, and the power is allowed to be negative. The answer part, the 8x, is not allowed to be negative, and the base is not allowed to be negative or 0 or 1. So in this case, I've isolated the logarithm, so now I'm going to switch forms. So I have 9 to the negative 1 power equals 8 times x. That's my answer part. And then to solve for x, I would divide both sides by 8. I can also think of this 9 to the negative 1 as 1 over 9, which will probably make it a little bit easier to come up with a solution that x is equal to 1 over 72. If I have x equals 1 over 72 and I plug it into the original, it will work. Again, 1 over 72 times 8 is a positive value, so it does work as the answer part. So it is not extraneous. Let's now look at problem number 14. In problem number 14, I've already got the logarithm isolated. I have a very complicated and long answer part, but it is already in logarithmic form, so I can simply switch forms. In this case, I'm going to get 2 to the second power equals x squared plus 3x minus 24. Multiply out the 2 squared to get 4, and then combine everything onto one side of the equation so you have 0 on the other. When I subtract 4 from both sides, I get x squared plus 3x minus 28 equals 0. Are there two factors of 28 that have a difference of 3? Yes, 4 and 7. Since it's a positive 3x, I'll need an x plus 7 and an x minus 4. This gives me two possible solutions, x equals to negative 7 or x equal to 4. I cannot box these up until I check to verify that they will work in the original problem. When I plug these into the original answer part, my original answer part was x squared plus 3x minus 24. If I substitute negative 7 in here, do I get a positive number? So I get negative 7 squared plus 3 times negative 7 minus 24. What does that equal? 49 minus 21 minus 24 is going to turn out to be, I think, 4, which is positive, so it definitely works. That is a solution. What about if I substitute in 4 to the answer part? I get 4 squared plus 3 times 4 minus 24. This gives me 16 plus 12 minus 24, which is 28 minus 24, which is also 4. Both of these solutions work in this particular problem. Neither one was extraneous. Even though the x is negative, when I substitute it in the answer part is not negative. And that's what makes it an extraneous if you have one. Now let's isolate and look at the natural log in problem number 15. I have the natural log of 5x minus 16 minus 7 equal negative 4. Before you say natural logs can't be negative, they can. That's the power. First, I want to isolate the natural log by adding 7 to both sides. And this will give me natural log of 5x minus 16 is equal to 3. Isolate the natural log, then switch forms. The base is e, and it's cubed, and it equals the answer part, 5x minus 16. Now solve the answer part for x. First, we add 16 to both sides, and we get e cubed plus 16 equals 5x. Then divide both sides by 5, so we get e cubed plus 16, all divided by 5, equal to x. We have to make sure that this does not cause the answer part to be negative or 0. So we check the original answer part, which was 5x minus 16, and we plug in this value into the answer part. So I have 5 times e cubed plus 16 divided by 5, and then minus 16. The 5's will cancel, and I get e cubed plus 16 minus 16, which gives me e cubed, which is definitely a positive number. So this is the solution to my problem. Now, if you want to have a decimal value, you'll have to use your calculator because e cubed is irrational. So if you do this one, then you're going to have e cubed plus 16, and then you're going to divide the whole thing by 5, which is going to give you about 7.2171, blah, 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 all right? And that should give you the same value on both sides when you plug it in. Now let's look at one that uses that equality property, that one-to-one property of natural logs. In problem 16, we have log base 11 of 6x minus 2 equal to log base 11 of 8 minus 3x. When we're looking at this, the two sides are equal, so the powers are equal because the logs are the powers. The bases are both 11, and because the logarithm is a one-to-one property, and I have one log equal to another log of the same base, then I know that the answer parts have to be equal. Then I need to get all my x's on the same side of the equation and move anything that doesn't have x in it to the other side. This gives me 9x equals 10, or dividing both sides by 9, I get 10 over 9. I need to make sure the original answer parts, both of them, do not turn out to be anything but a positive number. So I'm going to check 6x minus 2 by plugging in my possible solution, x equal 10/9. This gives me 60 divided by 9 minus 2. 54 divided by 9 is 6, and this is larger than that, so I know that this will come out to be a positive number. Now let's check in the other answer part. You must check both. All answer parts must be checked. Now when I plug this in, the possible solution, x equals 10 over 9, the 3 and the 9 will reduce and give me 10/3. So I have 8 minus 10/3. Then I write it as 8 over 1 and multiply by 1 in the form of 3 over 3, which gives me 24/3 minus 10/3, which comes out to be a positive 14/3. So it also works. That means that the solution 10/9 is a solution to the original problem. Whatever your solution is, it has to work in all original answer parts. Let's now look at problem number 17. Pause the video, work it out, then turn the video back on. Don't forget to check for extraneous or false solutions. In problem number 17, we have a natural log equal to a natural log, only one log equal to a natural log. The bases are both e and the powers are equal, so the answer parts have to be equal. This gives us a quadratic equation, which we can solve by factoring out the common factor of x. It gives two possible solutions, x is 0 or x is 12. I have to check both in both original answer parts. When I try to check x equals 0 in the answer part on the left, I get that 2 times 0 is 0. But answer parts are not allowed to be 0, which means that this one fails. I don't need to check it in the other one. If it fails either, it's out. That makes x equals 0 extraneous. Then I check the possible solution x equals 12 in both answer parts to ensure they give me a positive number. The first one gives me 2 times 12, which is 24, and is definitely positive. The second, when I square it and then multiply it by 10 and subtract from that, I get 24, which again is positive. That means the only solution to this problem is 12. Now let's look at a slightly different type. In this one, there are actually several different ways of solving it. But one of the easiest, because they're all log base 10, is to compress the two logarithms on the left and then use that one-to-one property like we did in the previous two problems. So let's take a look at compressing what's on the left. They're added together. They have no coefficients out front other than positive 1. And that enables me to write log base 10 of the product x times x minus 20. Make sure you keep the x minus 20 in parentheses. This then has to equal the log base 10 of the answer part 2x. So I compress the side with multiple logs to get one logarithm. And now I'm going to use that one-to-one property, which says if the logs are equal and the bases are equal, then the answer parts have to be equal. So this gives me x times x minus 20 equals 2x. Multiplying out the left, I get x squared minus 20x equals 2x. Move the 2x to the left side to get all our terms on one side. This gives us x squared minus 22x equals 0. Factor out the common factor. This gives us x times x minus 22. So two possible solutions are 0 and 22. Now, when we look at this, don't automatically discount 0. It depends on what we have in the original answer parts. When I look at this one, though, this first one right here, log of x, is going to exclude the x equals 0 because that answer part cannot be 0. So this one is automatically out. Now I need to check the other one. Is it okay to have log base 10 of 22? Yes. What if I were doing the next answer part, x minus 20? If I substitute 22 minus 20, I get 2, which is positive, so it checks. What about in the third one on the right side? You must check them all. 2 times 22 gives me 44, which is positive, so it checks. We have one solution, which is x equal to 22. On this problem, we can see right here that we have one logarithm or two logarithms on the left and none on the right. Can we solve this by compressing the two on the left? Yes, you can. So what you can do is you can write this as the natural log of x plus 9 times x minus 9 equal to 0. Once you've compressed the left side, you have one logarithm equal to a constant. So we switch forms and go to exponential. The base is e, the power is 0, and it equals x plus 9 times x minus 9. Now, e to the 0 is going to be 1. So if we multiply out our x squared, or our x plus 9, x minus 9, we know that we'll get the difference of two squares pattern, x squared minus 81. We have to get all terms on the same side, so we subtract the 1 so that we can get our polynomial all together. So we have x squared minus 82 equal to 0. Now the next thing we need to do is solve for x. So one thing we can do is, well, it doesn't factor. You could use the quadratic equation, but I don't have an x term. So I can isolate x squared, and then I can take the square root of both sides. Normally, this will give us plus or minus the square root of 82. So this gives me 2 to evaluate, the negative square root of 82 or the positive square root of 82. If I check the original and I look up here, I need to know if the negative square root of 82 plus 9 is positive or negative. So I'm going to have to think about this one for a little bit so that I can figure it out. Now I know the square root of 81 is 9 and 82 is bigger. So it's going to be more than 9, so 9 point something. And negative of that plus 9 is in fact going to be negative. And that tells me that this one cannot be allowed. It's going to be extraneous. Try the square root of 82, and this time we have to check in both. If I take the square root of 82 and I add 9, well, it's a positive plus a positive, so it's definitely positive. The only one that worries me is the square root of 82 minus 9, but 82 is bigger than 81, so the square root is larger than 9. So it's going to be very small, but still positive. So it does work, and we get one solution. Now I want you to pause the video, work this problem out in whatever method you choose, and then turn the video back on to compare your answer. This is an interesting problem because there's a lot of ways to solve this one. The way I solved it is probably not the way you thought of it first, but this is a good way to solve this problem. Let's take a look at this one and see what's going on and why I chose to solve it this way. Notice that on the left, I have both a positive and a negative. Now I can put those together, but it would be x minus 3 divided by x if I chose to work it that way. So if I did that, it would look like this. The x's do not cancel because the numerator is the x minus 3 group. The whole thing goes or none of it goes. And then this is equal to the natural log of 48. Then you can use the one-to-one property of logarithms to say that since the bases are both e and the power of the logarithms are equal, then you must have x minus 3 divided by x equal to 48. And then you can multiply both sides by x, and the next thing you need to solve is x minus 3 equals 48x. You'll see over here that is not actually what I did. In blue, what you'll notice is that I looked at this and said, well, it is negative here on the left, but if I moved it to the right, it would be positive. And I much prefer not having division. So what I did was I added the negative logarithm to move it to the opposite side where it became positive. Then I combined the two positive on the right into the natural log of 48x. Then I had a logarithm equal to a logarithm with the same base, so I set the answer parts equal. Then I went ahead and solved, and I got x is negative 3 over 47. Now this is a problem in 2 of our 3 answer parts. If it's negative, then it can't be used as the answer part for the natural log of x. It also can't be used for the natural log of x minus 3 because a negative minus 3 is definitely still negative. The only solution we got won't work, which means there's not a solution. These are graphs that never cross. Go ahead and work this problem out, then turn the video back on and we'll compare our answers. Take a moment, pause the video, and look over the work here to see if you can understand how I solve this problem. Again, in this problem, there are two possible solutions, but one of them is extraneous and does not work in the natural log of x, or the natural log of x minus 3, or even the natural log of 7x. In all cases, it either gives 0 for an answer part, which is not allowed, or a negative, which is also not allowed. Now let's move on to the last problem in our set, problem 23. Problem 23 is an application problem. It's a population growth, and since population tends to change continually, it is based on the exponential function e to a power. In this particular problem, we have the model P of t, population at a later point in time, given by 2200 times e to the 0.2t. 0.2 is our growth rate. 2200 represents the original population of the city. We want to know in how many years the population will reach 45,000 if this model continues to be accurate. So in other words, we want to know what the t is that causes the later population to be 45,000, growing from initial 22,000 at a growth rate of e to the 0.2. So when we're looking at this, what are we going to get? So our growth rate is the 0.2. So I'm going to isolate the exponential, just as I've done before. So I'm going to divide both sides by 2200. And notice that the two sets of zeros will cancel out. And then I have 450 divided by 22, which I don't know what that is. I know they're both at least divisible by 2, so I can do that much. So that would give me 225 divided by 11. 225 is a power of 15, so it has factors of 3 and 5, but not 11. So it's not going to reduce. So I'm going to stay with that improper fraction. And now that it's in exponential form, I'm going to switch to logarithmic form. My base is e, so I use natural log. The answer part is this 225 divided by 11. And the power which caused that to happen was 0.2 times the time period. Now, 0.2 is 1/5, so I can multiply both sides by 5. And when I multiply by 5, I get the value of t is equal to 5 times the natural log of 225 divided by 11. Now I have to use my calculator in order to figure this one out, since 225 divided by 11 is not a power of e. So I'm going to type in 5 times and natural log, open parentheses, 225 divided by 11, close parentheses, equals, and my time period is roughly 15.091, blah, blah, blah. Now they asked us to round to the nearest whole number, so we're going to round to 15, right? So 15 years at that growth rate is what it would take to go from 2,200 to 45,000. That's a really fast growth rate. I hope that this makes sense to you and that you have understood what to do. There is a lot of advantage to working additional problems. So I'm going to put on the screen a couple of different sheets that I've developed over the years that will help you to practice this process of solving exponential and logarithmic properties. So let me open those up for you. So here are a collection of problems that I have gathered over the years, and they do have extraneous solutions mixed throughout. So pause the video and write down at least 1 through 13 and 17 through 28. And then I'll unpause it and you can scroll down to see the last few. Here are the last few from 14, 15, 16, and problem number 29. Now unpause the video again, and we're going to take a look over here at the solutions. You'll want to pause the video in order to be able to write down these solutions. And I'm sorry they're not better written, but this was as close as I could get in the amount of time I had available. So pause the video and write these down, then I'll scroll to the bottom of the screen. Now we're scrolling to the bottom of the screen so that you can get all of the problems on here. Well, it looks like I'm going to have to shrink up the size a little bit. Right? And that should get you all of the different ones. If it has an X through it, that means it's an extraneous solution. It was a possible solution, but it does not actually work. I hope that you have enjoyed this video and this particular chapter on logarithm and exponential properties. We only have a little bit left to cover, which are just a few additional topics. We'll be talking about solving systems of equations and matrices in the upcoming videos. I hope you'll join me for those as well.